Hey guys, welcome to Chapter 8. This is Advanced Theories of Covalent Bonding. Now this chapter is only 4 sections, but we are doing it over 2 weeks because it's kind of heavy. So bear with me, let me know if you have questions. It's more of a conceptual type of chapter, so it's definitely different than what we've done so far. So we're going to talk about valence bond theory, hybrid atomic orbitals, multiple bonds, and molecular orbital theory. So we're going to talk a little later in this chapter about how oxygen gas, when exposed to a magnetic field, actually line up with a magnetic field instead of just not even interacting with it. So it's it's interesting. It doesn't do what we would predict it to do, because this is something that lone electrons, unpaired electrons, would do, is they would line up in a magnetic field. But oxygen has 2 sets of lone pairs. So we're going to talk about that later, I believe in section 8.4, but this is just to start getting your mind spinning. We've talked about VSEPR theory so far, and so we're going to expand on it and do some newer theories that are even more accurate than VSEPR. So we're first going to talk about valence bond theory. And in this, we're going to describe the formation of covalent bonds in terms of atomic orbital overlap, and define and give examples of sigma and pi bonds. So there are some general parts to valence bond theory, and some of this you already know. To form a covalent bond, an atom has to have an unpaired electron, so it can share electrons with another. The number of bonds formed by an atom is determined by the number of unpaired electrons. And this theory works very well for explaining the bonding in diatomic molecules with only single bonds. So diatomic meaning 2 atom molecules. It also works well for explaining why noble gases don't bond. So in the 1930s, Linus Pauling and some others developed valence bond theory of covalent bonding. So we know that electrons reside in orbitals, and our covalent bonds form when the electrons are shared by the overlapping of singly occupied orbitals. So you have, an s orbital with only 1 electron in it can overlap with another s orbital with 1 electron. So this forms an electron pair. And the more overlap you have of your orbitals, the stronger the bond. So if you have, 2 s orbitals and they're overlapping like that, okay, that's not bad. But if they have even more overlap, that's an even stronger bond because there's more interaction. And the distance between the orbitals and the orientations of the orbitals themselves affects this overlap that occurs. So we looked at this picture before, this graph of hydrogen molecule forming from 2 hydrogen atoms. As they get closer and closer together, they get this optimum overlap to get the lowest overall energy of the system. So again, overlap very much influences the strength of the bond, so the orientation and how much overlap there is. So these are 2 p orbitals that are overlapping in 2 different ways. So in A, you see this end-to-end overlap, and you see this very strong, large area of overlap. Whereas in B, the orientation of these orbitals make it so that this overlap is a lot smaller. Okay, this is the plus signs. These are the nuclei here in the center. Okay, so you can see now how that overlap influences the strength of a bond when it comes to orientation. So we have 3 different ways to form what is called a sigma bond. So sigma being this symbol right here. So you can either have 2 s orbitals, an s and a p orbital, or 2 p orbitals that are overlapping end to end. So this is a sigma bond, and these are always single bonds. So all single bonds are sigma bonds. And so what's happening is the electron density is concentrated in the region along the internuclear axis. And the internuclear axis is the line between the two nuclei that goes through the center of the overlap. Okay? So that's the internuclear axis. Okay, so along that axis is where the overlap is occurring, and that electron density is. Now, if you have two p orbitals overlapping side by side, what's happening is you have these two lobes of the p orbitals that are overlapping with each other. And this forms a pi bond. So these are double and triple bonds. So first you form a single bond, and then from there you can form pi bonds from there on. And then what also happens, because you have these two lobes, you have a node along the internuclear axis. So this node here, there's no electron density. So it's either above or below in one of those two orbitals. So again, multiple bonds. So if you have a double or triple bond, you have both sigma and pi bonds. There can only be one sigma bond in any one location though. So the first bond is always a sigma bond. The remaining bonds, whether they be double or triple bonds, are going to be pi bonds. So in HCl here, we have one sigma bond. So there's only a single bond there, no pi bonds. In oxygen, we have one sigma bond and then one pi bond for that double bond. And in this N2, in nitrogen, we have one sigma bond and two pi bonds. So in the example here, we want to identify each illustration as depicting a sigma or a pi bond. So in A, what we see is side-by-side overlap of a 4p and a 2p orbital. So when you look at this, what you see is you have side-by-side, and you have this overlap with a node in the center. That means this has to be a pi bond. And you don't even need the pictures to figure these out either. In B, we're told end-to-end overlap of a 4p and another 4p orbital. So this is end-to-end, okay? And this is along the axis, the internuclear axis. So this is going to be a sigma bond. I usually make prettier sigmas. Let's see. There we go. And C, we have another end-to-end overlap. This time it's a 4p and a 2p orbital, but again, end-to-end along the axis. This is also a sigma bond.